signature. And and we have some forecast about the observability of the signal from either the CMB polarization measurement like Lightbird or the future 21 centimeter tomography for the dark ages mode. And there are actually other ways if you go beyond the minimal slow roll setup to get large signals. For example, in this paper, the authors study whether the classical excitations, the features, can generate large signals. And this shows that by this additional energy injection into the graph, it's possible to generate large signals, even the intermediate particle is very heavy. And beyond this, there are also other ideas, like we can make use of the finite temperature effect, or we can consider the so-called curvaton mechanism. And also we can even think about whether these signals can be measured from the dark matter isocurvature. These are the related works if you are interested.
Hi, we have 2 minutes.
2 minutes? Okay, I will be fast. Sorry, 2 minutes, right?
Yeah, 2 to 3 minutes.
Okay, good. So there are also ideas using the modulated reheating to enhance the signal size. And we have this so-called cosmological Higgs collider, which are actually measuring the Higgs interaction. And this can also be used to probe several key ingredients of the leptogenesis. Since my time is up, maybe let me just quickly comment on the challenges of this program. The most serious challenge, as I see, is we need to efficiently and reliably compute these correlators, which turns out to be quite non-trivial. And in recent years, we have spent a lot of time and some efforts, both in numerical computation shown here, and also some analytical method to compute these correlation functions. There are several directions. One is the so-called partial Mellin-Barnes representation. That is, we transform everything into the Mellin variable. The good thing is that all the complicated time dependence will be eliminated, and all time dependence will just be resolved into simple powers. And the difficulty is translated to the completion of this Mellin integral, which can always be done using complex analysis by using the residue theorem. Another method which is fast developing is the so-called cosmological bootstrap. The idea is that instead of computing complicated Schwinger-Keldysh integral, we simply derive a differential equation for it. Then by solving this equation, we can get the result as well. So by exploring these two analytical methods, we are able to get a complete analytical and closed formula for a class of tree-level cosmic correlators with massive exchange, and also with the presence of chemical potential. Here are some simple formulas, and also the plots derived from this analytical expression. So previously, if you do this numerically, if you want to compute a loop process, maybe you have to run your codes on a cluster for weeks. But now with the full analytical result, you can do this on your laptop within seconds. And you can also explore the parameter dependence of the signal given the full analytical result. I will skip some of this. And finally, there is a new effort in computing the loop diagram. So here the idea is that we can make use of the existing spectral decomposition techniques to collapse a loop diagram into an integral of tree-level diagram over mass. And now that this so-called spectral function and the tree-level correlators have been computed, we can put all these ingredient together and to finish this so-called spectral integral and get the final full analytical result for the loop. Here are some plots. I guess I'm running out of time, so let me just go to my summary slide. I want to give you some simple take-home message. First one, the cosmological collider physics is a promising new direction for exploring fundamental new physics at ultra-high energy scale. And second, there have been many new ideas put forward recently in the phenomenological studies, but more efforts are called for to fully explore the potential and to explore the new possibilities. And finally, the analytical understanding of QFT amplitudes in de Sitter space-time is a much unexplored area. And there are some notable progress recently. And I think this is important for both theory and for phenomenology. So I guess I can stop here and I will be happy to take questions. Thank you.
Thank you for the nice talk, Zhongzi. So now we have some time for question answer from the audience. If anybody wants to ask any question, please unmute yourself and ask. Yes, Daniel wants to ask a question. Please go ahead.
Yes, can you hear me? Yeah.
Yes.
Thanks for the nice talk, Zhongzi. I was wondering, you brought up also the case of axion inflation, but it's not clear to me, or maybe I just misunderstood, what is new in the computations you guys are doing in axion inflation, in the sense that before there was this program of cosmological collider, people were already looking, of course, into what are the constraints you can put into the axial coupling, no, say between the inflaton and ether dual, because this induces non-Gaussianity in the scalar sector, and this has been constrained by Planck. So what is exactly what you are guys doing new, just for me to understand?
Good, very good question. Sorry, I was not very clear. So the message here is that we can use the axion as a source of particle production. So axion, the rolling of axion, if the axion is an inflaton, can be a source of particle production. A new thing here is that the produced particle, the daughter particle, can be massive. And once they are massive, we can generate oscillations, and we can measure their mass. This is the new message.
I see. But then I'm guessing, are you thinking about massive gauge field, or you are thinking about massive gauge field also? Okay, I see.
Either gauge field or fermion, or even massive spin too.
Got you. Okay, thank you very much for the clarification.
Thanks.
Any other question from the audience? If not, then just one small curiosity I have. So you talked about the non-Gaussianities only in the squeezed limit, right? Local non-Gaussianity in the squeezed limit. So
right.
I mean, is there any program to go beyond this, and what are the challenges that lie if you want to actually look at the shape of the Gaussian? I mean, lots of rich structures that may exist in the non-Gaussian.
Yeah, theoretically, the squeezed limit is certainly the most interesting one. But if you move away from a squeezed limit, I can mention two things. First is that there will be interesting deviations. Yeah, thanks for bringing this up. Let me go to that slide. If you move away from a squeezed limit, you will see deviations from exact sinusoidal signals. Sorry, where is it? Must be. Sorry, I cannot find it. But let me just say in words. You will have deviations from exact sinusoidal signals, and that is here. So these deviations can be used as a way to distinguish different intermediate particles. So otherwise, we will have no ways to tell the difference between the scalar and the vector loop. Their structure are pretty similar, and frequency only tells the mass. But this deviation from exact sinusoidal signals can contain a lot of new informations. So the challenge here is that whether you can compute this evolution of phase reliably. This phase can be, by the way, can be measured in any case, as long as you can see the signals, right? So once you can read the phase out of the signal and you can compute them, you can make use of this to break some degeneracy in your model. That's one thing. The other thing is that there are also some recent study, I believe, in this pair of papers. These authors discuss the effect of non-unit sound speed, and they realize that in the non-squeezed limit, the non-unit sound speed will excite some interesting new oscillatory behavior, some new shape, which are also interesting. That's all I can say about non-squeezedness.
Okay, thank you. Thank you. Yeah. Okay, let's thanks the speaker one more time for this talk, and let's move on to the next talk of the day.
Okay, thank you. Thank you.
Isuke, are you available?
Yes, I'm here.
Okay. Nice. Yes, we can see your screen. So today,
okay.
Yeah. Okay. So let's start with the third talk of the day, which is the last talk of the morning session. And we have Keisuke Inomata from Chicago, and he's going to talk about gravitational wave induced by scalar perturbations in early universe. I'll send you a reminder when 5 minutes are left.
Okay. Can you hear me?
Yes, we can.
Okay. Yeah. Thank you for the introduction. I'm Keisuke Inomata. I'm a postdoc at the University of Chicago. First of all, I'd like to thank the organizers for giving me this opportunity. I'm very happy to be here virtually. So in this talk, I'm going to talk about the gravitational waves induced by scalar perturbations in our universe. And this talk is based on these papers. Okay, so now let me begin with the introduction. Scalar perturbations are one of the most important quantities in cosmology. So scalar perturbations are origin of many things like large-scale structure and the Symbian isotopies. From the observations, we already know the amplitude of the scalar perturbations like this. And the scalar perturbations originates from the vacuum fluctuations of field during the inflection era. So scalar perturbations have a lot of important information of our universe. Okay, so in this talk, I'm going to focus on the gravitational waves induced by scalar perturbations. So let me explain that. So in the Newtonian gauge, metric perturbations can be written as this. So these are scalar perturbations, and this is tensor perturbation, which describes gravitational wave. And so substituting these second order expression of Einstein tensor and energy momentum tensor into this Einstein equation, we finally obtain the equation of motion for tensor perturbations. Point is that right-hand side is the source term, which comes from the second order or square of scalar perturbations. Okay, so scalar perturbations can induce gravitational waves at second order, and I'm going to focus on this kind of gravitational waves in this talk. And here, let me mention when large gravitational waves are induced. The most famous one is the large curvature power spectrum. In the context of primordial black holes, we often consider large curvature power spectrum. Once we consider such kind of large curvature power spectrum, large induced gravitational waves are produced. This is obvious because induced gravitational waves are proportional to the square of scalar perturbation. Like if we consider this kind of power spectrum for the previous scenario, large gravitational waves are produced like this. But in this talk, I'm going to discuss other cases for the large gravitational waves production without large curvature power spectrum. So this figure shows the evolution of the source scalar perturbations And the first scalar perturbations are inside the horizon. And even, so this is during the inflation. And even during the inflation era, large gravitational waves can be induced by the scalar perturbation. So I will talk about this in the second half of this talk. And after that, scalar perturbations exit the horizon and the inflation end, and they re-enter the horizon. In some situations, large gravitational waves can be induced after the inflation. I'll talk about that in the first half of this talk. Okay, so now let me move on to the first topic, gravitational wave production right after reheating. Before going to gravitational wave, let me briefly explain primordial black hole. Primordial black hole is the black hole produced by a large density perturbations in our universe. So let me explain the PBH production with this schematic picture. So this is after the inflation. First, perturbation scale is larger than horizon. Afterward, the perturbation enter the horizon. I mean, scale of perturbation is comparable to horizon scale. And if density perturbation is large enough, like 0.1 during the radiation dominated era, the large density perturbation collapse into black hole. Yeah, primordial black hole like this. And the primordial black hole mass is the mass inside the horizon. That means the PBH mass is determined by the scale of density perturbations. So that means the PBH can have a variety of masses like this, like a 30 solar mass for the LIGO Virgo events, and 10 to the 20th gram PBH can explain dark matter, and the PBH with the mass lighter than 10 to the 15th gram disappear by now through the Hawking evaporation. So this is a primordial black hole. And so in this talk, I'm going to show large gravitational waves can be produced right after sudden reheating at the end of RE matter-dominated era. So this is a fiducial scenario. So first inflation occurs, then reheating occurs, then RE radiation dominator begins. And I assume that a lot of tiny primordial black holes are produced during the RE radiation dominated era. And afterward, the PBH can dominate the universe because the energy density of the PBH behave as a non-relativistic matter. So PBH can dominate the universe, but the tiny PBH evaporate at some point. Then radiation dominated begins again. And so large gravitational waves can be produced right after the PBH evaporation. And large gravitational waves are produced by the scalar perturbations that enter the horizon during the PBH-dominated era. Okay, so let me show you the evolution of the scalar perturbations like this. Okay, so this figure shows the evolution of the quantities. Horizontal axis is the conformal time, so time goes from left to right. And the blue and orange dot dashed line shows the energy density of radiation and the matter PBH energy density. So first, universe is dominated by the radiation. But at some point, the PBH dominates the universe, then PBH dominated begins. And afterward, the PBH evaporates. So then radiation dominated begins again here. And these two green and the cyan dashed line shows the evolution of the gravitational potential with different wave numbers. And the large scale means the smaller scale. And the smaller scale perturbations enter the horizon area. So point is that during the PBH-dominated era, gravitational potential doesn't decay. So gravitational potential is constant. But after the reheating, they start to oscillate because of the radiation density perturbation oscillate due to their pressure. And point is that the oscillation time scale is determined by the wave number of the gravitational potential. So if we consider smaller scale perturbations, the oscillation time scale can be much shorter than the Hubble time scale. And here, let me compare this result with the other cases with the constant decay rate. So right figure is the same as the previous one. And the left figure shows the result with a constant decay rate. So So these are the gravitational potential with different wave numbers. And let's focus on this cyan dashed line because they have the same wave numbers with the normalization with the conformal time at equality time. And we can see that there's a large suppression before the oscillation. So there's a 10 to the minus 15 suppression here. On the other hand, this is just a 0.1 suppression. And this is because during the reheating, the fluid deviates from the perfect fluid because matter and emitted radiation are not strongly coupled. So effectively, there's anisotropic stress, and then perturbations are dumped. So this is similar to the diffusion damping of the late time. And this means that the longer reheating period leads to larger suppression like this. And I'm going to show you the last gravitational waves it's from this fast oscillation. But these suppressions are suppressed of the gravitational production. And so this suppression must be small to realize a large gravitational wave production. So we need to consider this kind of sudden reheating, like a PVH evaporation. Okay, so now let me explain the gravitational wave production. As I said, the fast oscillation of the gravitational potential is important because equation of motion for tensor perturbations is given by this, and source term is given by this. And the point is that these terms have a time derivative, and this can be approximated as this. And as I said, the oscillation timescale is determined by the 1/k. So if we consider smaller scale perturbations, so this factor becomes much larger than unity. So this enhances the production of gravitational wave. Then large gravitational waves are produced. Okay, and now let me explain a little bit about physical interpretation. Actually, we named this enhanced mechanism the poltergeist mechanism based on our physical interpretation. Okay, let me explain that. So this is the schematic picture, and through the reheating or decay of the non-relativistic matter, density perturbations becomes radiation density perturbation. And after the decay, ghosts of the non-relativistic matter make a noise in the thermal bath. And the ghost corresponds to produced radiation, and make a noise corresponds to the oscillation of radiation sound wave. Then large gravitational waves are produced. So this is the physical interpretation of this mechanism. And so let me show you the gravitational wave power spectrum. So as of this example, I consider this kind of curvature power spectrum. So this is almost scale invariant, but we introduced the cutoff scale here. So we introduced the cutoff scale here because if we consider very small scale perturbation, the density perturbations can be larger than unity because density perturbations, so once density perturbation enter the horizon, the density perturbations grows proportionally to the scale factor during the matter-dominated era. So if we consider very, very small scale, the density perturbations becomes non-perturbative. So we cannot use the perturbation theory, but in our calculation, we use the perturbation theory. So in order to get the conservative result, we introduce a cutoff scales. So in this sense, our result might be to, how should I say, might lead to the too small gravitational waves. So if we take into account non-perturbative effect, these result, gravitational waves might be larger than this result. Anyway, so we use this power spectrum, then we get this result. And so we fix the length of the PVH dominated era, and we change the PVH mass. And the lighter PVH corresponds to the earlier time. Lighter PVH evaporate at earlier times, and the earlier time corresponds to the smaller scale, and the smaller scale corresponds to higher frequency. So that's why we can see higher frequency gravitational waves for the lighter PVHs. And the thick line corresponds to the case where the all PVH has the same mass. And the thin line corresponds to the finite with mass function case. So if we consider finite with mass function, the each PVH has a defined mass, and that effectively leads to the makes the heating more gradual. So then gravitational waves are suppressed. And actually, so this kind of enhancement mechanism is used in these papers. So, okay, yeah. So now let me move on to the next topic, gravitational wave production during inflation. So before going to the gravitational wave, for my work, let me mention the sources of gravitational waves during the inflation. So the most famous one is a quantum fluctuation of tensor field. So this is the target of B mode observation of CMB, and the first order phase transition can also induce the gravitational waves through the bubble collision, and the gauge fields coupled to a rolling scalar field can induce the gravitational waves, and the scalar fields can induce large gravitational waves during the inflation, like a field with a small sound speed, and also the features in the potential of the sound speed and the rapid time that field projects really can induce large gravitational waves. And I'm going to propose a new case where the oscillation of the spectator field induce large gravitational waves. Okay, and this is the situation. So I'm going to discuss these situations where the spectator field starts to oscillate during the inflation. And I consider this kind of potential as a fiducial example. And so this is an infraton potential. So this is a linear potential, but this is not so important here. The most important part is here. So this is the spectator field potential. And I consider alpha attractor type potential as a fiducial example. So if we consider this kind of potential, the oscillation of spectator field leads to the parametric resonance of the spectator field fluctuations. Okay, so let me explain why spectator field fluctuation are resonantly amplified. Okay, so left figure shows the evolution of the quantities. And the x-axis is the E folds, and the N0 corresponds to the time when the spectator field passes through the origin. So spectator field starts to oscillate at some point. And once the spectator field starts to oscillate, effective mass of spectator field also starts to oscillate like this. Dashed line means the negative mass. The oscillation of the effective mass leads to the parametric resonance of the spectator field fluctuation. So this is the square root of the power spectrum of spectator field fluctuation. And so once the spectator field starts to oscillate, the perturbations gets resonantly amplified. These three lines have the different wave numbers, and the orange line corresponds to the peak scale perturbation. But at some point, the resonance stops. This is due to the Hubble expansion. So Hubble expansion decreases the mass amplitude of the mass oscillation like this. So at some point, the resonance stops. And the right figure shows the snapshot of the spectator field power spectrum at the time when the peak scale reaches a maximum. Okay, and I change the parameters like this, and we can see that so enhancement is sensitive to this alpha parameter. So alpha controls the m chi over h if we fix the V0, delta V over V0. So parametric resonance is sensitive to the parameters, exponentially sensitive to the parameters. And I also show the case with the lower energy scale inflation. So this is much lower than the fiducial case. So these lines correspond to these parameters. But even if we consider very low energy,
we have 5 minutes left.
5 minutes. Okay, thank you. So even if we consider the lower energy inflation, we can still realize a large enhancement if we tune the parameter alpha. But too large mass causes a back reaction problem if the perturbation amplitude is larger than the background oscillation amplitude. So in some sense, this is a very marginal case. Yeah, so perturbation is close to the background value. And if over H is fixed, a larger delta V over V0, which can be approximated as this, leads to a larger enhancement, larger amplitude of the background oscillation. So large delta V over V0 is required for the large enhancement within the perturbative regime. Though if delta V over V0 becomes larger than unity, the situation becomes different, because in that case, the potential of a spectator field dominates the universe. I mean, once the spectator field starts to oscillate, the universe is dominated by the oscillation energy of the spectator field. I think in that case, we should not call that field spectator field, because the potential energy of spectator field is larger than inflaton potential energy. Yeah, in that case, the situation becomes different, and that's beyond the scope of this work. Okay, and yeah, finally, let me show you the gravitational wave spectrum. Okay, so using this power spectrum of the spectator field fluctuation, and using this equation motion, I calculate the gravitational wave. So this is the result. Of course, it depends on the parameters, and so we can see that. So if we change the parameters, the gravitational waves might be might be investigated by the future observations. And I also calculate the curvature power spectrum like this. And we can see that so there's a little feature, but there's no large enhancement of the curvature power spectrum, but still large gravitational waves can be produced. And a similar gravitational wave production mechanism is discussed in the context of reheating after the inflation. Yeah, so these papers and today's Figueroa talk is talking about this. And this kind of gravitational waves could be used as detectable traces of a heavy field that is not coupled to any other fields. So I think this is the interesting point of this work. Okay, so let me summarize my talk. So I have talked about two topics. One is the large gravitational wave production right after sudden reheating. So in this case, the main source comes from the fast oscillation of the scalar perturbation after the sudden reheating. So this is evolution, and that this fast oscillation leads to the large gravitational wave production. And the second is the large gravitational wave production during inflation with spectator field oscillations. So if we consider this kind of potential, the oscillation of the spectator field leads to the parametric resonance of the spectator field fluctuation, and amplified spectator field fluctuation induce large gravitational wave. Okay, so I stop here. Thank you.
Thank you for the nice talk. Now we have time for some question answer from the audience. If anybody wants to ask any question, please unmute yourself now.
Sorry. Yeah, I have a question. So thanks for the talk. It was very nice. So in this first topic, your omega GW, what do you assume, like for the tensor to scalar ratio in the inflation sector, say? I mean, this flat line that you have.
Actually, okay, so this flat line comes from the second order scalar perturbations. So I don't write the first order gravitational waves. I mean, so this is comes from the fast spectrum of the CMB. I mean, scalar perturbation of CMB scales, like p zeta equal 10 to the -9. Yeah, so that scalar perturbation induced the gravitational waves. Yeah, so this gravitational wave is from the second order scalar perturbation. So we don't assume any inflation energy scale here.
So what sets this value of omega GW? The lowest value, I mean, not the enhancement, this where your cursor is. What sets that value? Why is it not bigger? Why is it not higher?
Here, you mean the lower? Okay, yeah. Actually, so this is determined by the scalar perturbation amplitude. And we already know the curvature power spectrum on CB scales. P zeta is 2 times 10 to the minus 9th. That determines the amplitude of the gravitational waves here. Yeah.
Okay. Right. Okay. Okay. And so in the second part, why didn't you just use a massive field, just m squared chi-square, rather than this alpha attractor, which?
Yeah, that's a good point. Actually, yeah, this is just a simple example. But if we consider phi squared, chi-squared, or something like that, yeah, similar kind of resonance occurs and the gravitational waves might be produced. I think that's an interesting future direction. Yeah, but in this case, this is just a future example, yeah, simple example. So even if we consider just no coupling, yeah, even if we don't assume any coupling of the fields, but still gravitational waves can be produced. Yeah, that's a good point. Thank you.
Okay, thanks.
We have one more question from Yanis. Yeah, you can ask.
Thanks for the very nice talk, Keisuke. I would like to ask about the first mechanism, the one that you call poltergeist.
Poltergeist, yes.
There, I think there was one slide that you gave a value of the spectrum of the scalar perturbations, and this value was the value that the CMB that we measure at the CMB scale is 10 to minus 9. Ah, this one, yeah.
Yep.
But in your mechanism, you assume that there are primordial black holes around. So there must be a peak in the power spectrum in order to have the production of these PBH.
Yeah, thank you. Yeah, good question. Yeah, actually, we need to assume some large power spectrum to produce tiny PBHs. Actually, the scale is much smaller than these scales. I mean, okay, let me show you the gravitational wave. Give me a second. Yeah, actually, so we need to consider the smaller scale power spectrum here. And yeah, I think so we need to we need a large curvature power spectrum around here. Yeah, so but we introduce a cutoff scale under here to when we calculate the induced gravitational waves. And in some sense, so there might be some gravitational waves under here from the non-perturbative density perturbations. But yeah, this is just a conservative spectrum.
Okay, so in your model, I think you make a very distinct prediction that you have two peaks in the spectrum of gravitational waves. But I'm understanding that this, as I see here, the spectrum associated with the PBH formation is at the very high frequencies. Huh?
Yeah, actually, so let me mention other sources. Actually, so evaporation PBH itself can emit the gravitons. Actually, so we also calculate the gravitational waves from the Hawking radiation, and there's a peak on here. And I also calculate the merger of gravitational waves. I mean, tiny PBHs merges, and such kind of mergers of the tiny PBH can produce the gravitational waves like this. And this gravitation comes from the large curvature power spectrum. And this is the gravitational waves from the poltergeist mechanism. So there are many peaks in this scenario. Yeah.
If I have a time for just a short question, you said that this enhancement of the gravitational wave spectrum comes from actually from the radiation domination era and not from the PBH domination era. So it's after the reheating of the the universe, and then it's due to the oscillations of the gravitational potential. So
Yes.
if we assume that the linear perturbation theory breaks down during the PBH domination era, you said that you expect that the signal should be enhanced. So it's a conservative estimation what you gave us. Yes, but I don't know. Probably you are correct, but since this enhancement comes from the oscillations of the gravitational potential, I think that maybe a nonlinear regime will significantly influence, these oscillations. But okay, I mean, this is something.
Okay, yeah. We can discuss later. Yeah.
Yeah, I don't have something. It's just I don't, because it's very interesting what you say, but I'm wondering how sensitive is this to to the transition from linear to non-linear regime.
Yes.
But,
you. Okay. Sorry. Okay.
Sorry, if I may just ask Chris, so why do you say that you cannot trust your cosmological linear perturbation theory in a PBH dominated era?
I think Keisuke knows there, yeah.
I don't say perturbation theory is not reliable in the PBH dominated era.
So probably there is a K value beyond which you cannot trust, but probably so you can trust it. So he's cutting off the spectrum at some point of time, right? He's cutting off spectrum. For example, in his case, I can see 450, right? So this is probably the point of time he can. I mean, beyond that, the non-relativists take over. So I don't think you can just simply. I mean, you can still trust the linear perturbation theory to some extent.
I agree on this. I totally agree. I said beyond that scale, what's going to happen? That's all. I mean, this the result is. I agree.
Yes, I think you are interested in the very small scale perturbation.
Yeah. Yes.
I think that's an interesting point. Yeah. But I'm not sure if we can. Yeah, we can believe that perturbation theory can give a reliable result in that case, that regime. I'm not sure if, what happens in this regime. But I agree, that is a very interesting point.
Okay, Keisuke, thank you a lot for the answers and very nice talk.
Yeah, thank you for the questions.
Okay, let's thank the speaker one last time. So we have now 30 minutes break. We will rejoin from 5 p.m. CET time. For our second session, we will have 2 more talks and then the final discussion session.